Hello everyone, we're going to go let me go to the top. We're going to start with question 1. We're given two different types of chromosomes, a normal chromosome, which here is displayed in green, and an inversion chromosome, which is in blue. We know that they're going to replicate, so there will be 4 of them, but we also want to see what would happen if there's a crossover between S and T. Now, if you're like me, you probably thought at first that this was the proper way to do it. You just put the 2 parents, and then you cut them wherever S and T are, and you put the ends on the opposite chromosome. It turns out that's not the proper way to do it. First, you look at your parent. You've got your first parent is product number 1. And here for product 4 is the other parent, but it looks different because it's reversed. We do that so that the S and T portions of this chromosome can align, which is needed for them to switch parts of the chromosome. And then we do it like we would have done it above, and we just take the ends and put it on either chromosome. And this gives us what we would expect for a paracentric inversion. You have 2 centromeres for product 2 and no centromeres for product 3. So a dicentric and an acentric chromosome, and that's what we would expect. For part 2, we're filling in the blanks. For part A, non-disjunction in meiosis 2 produces 50% aneuploid gametes. If this were non-disjunction in meiosis 1, all of them would be aneuploid. They're all messed up. So we know it has to be meiosis 2. Non-disjunction in mitosis can produce a mosaic phenotype, which is, it'll display different types of chromosome expression, such as haploid, diploid, triploid, all within what it codes for, such as skin, but in different areas. For part B, we want to know what produces a dicentric and an acentric chromosome. If we remember, we just that we did find a dicentric and an acentric, and it was a paracentric inversion. So we put that as the answer. In part C, we're looking at Turner syndrome. It's caused by monosomy, so there's only one X. And for the following portion, we know that familial Down syndrome is an example caused by Robertsian translocation. If they just said Down syndrome, it would be because of trisomy, but familial Down syndrome is due to translocation, not another chromosome 21. For part D, we're looking for the chromosome for types of cells that can have different chromosome numbers. And in the lesson, liver cells were mentioned. They can be 4N, 8N, or 16N, which is quite amazing, and it helps them to be more efficient. Part E, we're wondering what disease is caused by a terminal deletion in chromosome 5. And if we look at the notes, we realize it's Cre-Ducat syndrome, the one that produces infants. And then type A hemophilia is caused by inversion. So we see that there can be either manipulation through loss or gain of chromosomes, or just a change in structure can even cause a disease. For part A, we want to know what's going to change chromosome structure and could possibly be beneficial to an organism or an entire species. And we have to look back at the mentioning of gene families. Gene families can be beneficial, and they are created through duplications of pieces of chromosomes. So that must be the answer. In part G, we're wondering what kind of translocation cross would produce viable gametes and offspring. We know that alternate segregation is very common, and it also produces viable gametes. For part 3, we are counting chromosomes for the first part. We're wondering what the total number of chromosomes would be in humans if certain things happen to them. So for Turner syndrome, we remember there's one less X chromosome. So we have to subtract 1 from the total of 46, and that gives us a result of 45. For Jacob syndrome, we have too many chromosomes. We have one more than we need, so it's 47 chromosomes as a result. For Creutzfeldt-Cat syndrome, since it's just a deletion on part of a chromosome, it's 46 chromosomes. For familial Down syndrome, it's also 46 because it's occurring because of translocation and not because of trisomy, as we mentioned in the previous question. For type A hemophilia, we remember that it's just a structural change. There's no loss or gain in chromosomes, so it will still be the regular 46 chromosomes. For part B, we're looking at specific diseases and finding the terms that are not associated with it. So the Charcot-Marie tooth disease, type 1A, we're trying to find out what's not associated. That would be triploid, aneuploid, reciprocal translocation, trisomy, and non-disjunction, because we know that it's actually caused from the two remaining terms, diploid and duplication. For part C, we're looking for something similar. We're doing it with Klinefelter syndrome, but this time we want to know what actually is associated with it. Aneuploid fits because there's an abnormal number of chromosomes and an extra X. For trisomy, that is the term that explains that extra X. Non-disjunction is associated because one of the parents had to have a non-disjunction event. Otherwise, there could not be an extra X. So it was probably the female because she has a lot. It'd be more likely. For part D, we're looking at type A hemophilia again. We know it's a change in structure. And that change occurs through duplication. It also could mention inversion, but it's not on the list, so we know that it's just duplication. For part 4, we're actually going to be looking at a translocation cross for mice. So first, what we want to do is we make a cross, and we put one parent on the left side of the top and one parent on the right side of the top. And then we want to put below them the genotype that is associated with the parent. So we'll put the D's on the left and the M's on the right. And then, to make it easier on ourselves, we're going to put arrows that show the different kinds of crosses. And that'll help us with the following problems. For part B, we're wanting to do an alternate segregation cross. And we know that that's the orange arrows, they're diagonal. So you just go diagonal and you place them together, and that gives you your allele composition. Same thing with part C, except you use the red arrows because it's an adjacent one segregation, which means the top and the bottom are flipping. And for part D, you look at the blue arrows and you flip them again. For part 5, it's nice. It's like part 3, part A of part 3, where you're counting chromosomes again. So we're told that cats have a total of 38 chromosomes, but then we're going to look at different situations and see if that's changed. So if a cat is triploid, that would mean it has 3 sets of chromosomes. And if they have a total of 38, which we know is 2 sets, we just need to divide 38 by 2 to get 19 to find out how much is in a set, and then add it to the 38 to get 3 sets for a total of 57 chromosomes. Now, a cat that's monosomic for chromosome 12 means it only has 1 chromosome 12. So we know that there's going to be 1 less. cat that suffered a terminal deletion on a chromosome means it's going to be missing a chromosome. So again, it will be 37 chromosomes. But for part D, when it's a Robertsian translocation between two chromosomes, we still have a total of 38, because although we were shuffling around genetic material, we didn't actually add or subtract chromosomes. For part E, we are looking at a reciprocal translocation, and it's the same as D. Although it's shifting genetic material, it's not adding or subtracting chromosomes. I hope that this was helpful and that you can hear everything well. I already made this once and you couldn't hear me. So if you have any questions, feel free to post them. Thanks.